dedicate this class to the millions of fans who are going to watch this on YouTube. I'm assuming the lack of questions means that everyone is question-free. The last thing we did, besides the test, this from Monday,
I would think so.
we were doing the thing going up the ramp.
It's weird, oh no, this is notes that I did for myself. This is a different class.
Okay, so we did object going up ramp.
I think so.
All right. So let's actually talk about friction and relate it directly to, let's say, the pre-lab and the lab that you just did. We talked about the bits and pieces, but let's get more formal. All right. Box solid surface. So if I push on an object here, it should be moving to the right. In theory, or it depends on the total force is acting here. So if we do a force diagram, we have weight acting down, we have normal force acting up, we have this external force acting to the right, and then there's friction acting to the left. Whether it moves or not depends upon how much force is being applied. So let's zoom in on a little piece right here. Take a gander at it. We have two surfaces that are meeting each other. So as you zoom in, you get these little nooks and crannies, usually not violating laws of physics. You get nooks and crannies for one surface, and then the other surface that ultimately, if you zoom in far enough, it is definitely not smooth. So sort of the two views of friction are, there's what I refer to, and I don't think anyone else does, the nook and cranny model, where you've sort of like a puzzle here where you have two pieces like that they're basically running into themselves. You have this piece right here that's going to hit that, or this is going to hit that. There's some interlocking pieces there that really make it difficult to move. Now, how interlocked they are depends on how tightly pressed they are. And so if I think about this calculator sitting on the table right there, what is the force which signifies how tightly they're pressed together?
Force due to gravity?
Weight.
It is not the weight, because if I think about that, I used to have a stack of books up here, so we'll grab some just because it's simpler, at least in my head. All right, so I have a book right here. Instead of calculator, we'll do book. Right now, there's the book and the table are pressed together. I hope you can accept that. We can demonstrate that there must be something there, because if I push on it, it does stop. And Newton's laws tell me that there has to be some net force acting on it in order for the velocity to change. So think about this book has a certain weight to it. And now I put these on top. Has the friction increased or stayed the same or gotten less between the book and the table?
Stay
Right?
with it.
Increased, maybe?
When it's
Say
at,
it with confidence.
when
Okay,
it's at
increased.
rest,
Pardon?
when it's at rest versus moving, or should that answer be the same?
That's a separate thing that we'll talk about. But the weight, so the friction increases, and we can demonstrate that by push on that. It doesn't go as far. Has the weight of this book changed at all?
No.
So weight is not the thing that is affecting the friction.
Would it be the normal force then?
It is indeed the normal force.
Okay.
Because the greater the normal force means that there's more force trying to keep them from basically going through each other. The more normal force, the more they sort of get interlocked. So one of the things that affects friction is normal force. The other thing is the surfaces. You know, how rough the surfaces are really depends on what you're doing. And so if you actually look up some of this information for what's called the coefficient of friction, you have to look it up by two objects. Ice on ice, or plastic on wood, whatever it happens to be. So friction depends on normal force and this thing that is the coefficient of friction. Now, years ago when I was teaching high school, years ago, decades ago, when I was teaching high school, I had them sort of they created their own friction lab. And as they were doing friction, they noticed that it was getting easier and easier as they were doing the experiment. And part of it was that as they kept doing experiment after experiment, the surfaces started changing. Because like sandpaper, use sandpaper, the grit is going to start coming off of it and become smoother and smoother. And so their friction was dropping the more they did the experiment, because this was changing. This is a number that is depends on both surfaces. And so we have this generic formula. We're going to fine tune it in just a moment, of basically just the coefficient times the normal force. Or mu would be the friction force divided by the normal force. Now the way that they find this value of mu, it's found experimentally, it's not a theoretical thing. The experiment is really rather simple. You take the surfaces that you're involved in. So if I'm doing, I guess there's sort of a plastic cover to this, or plastic coating, and imitation wood. There's a prediction of, I know the weight, so W sine theta is the force down the ramp. I can then predict how long it's going to take for it to go that distance, or I can time how long it goes the distance. I can find the acceleration. Therefore, if I know what the force of gravity down the ramp is, I can then figure out how much friction there is. W cosine theta will be equal to the normal force, and then I can find my coefficient. The only difference between that I just outlined, so if I did this and we ran this experiment, hopefully it'll go. Thank you, Justin.
Mm-hmm.
When you put your hand out, I just trusted you were going to stop it. The difference if we did that experiment versus the people who do it and publish this stuff is their measuring devices are are more sophisticated. But that's the essence of the experiment right there. Now, let's get into something that Anna had mentioned, moving or not moving. If you'll notice, as I push on this table, the table does not start sliding. I'm applying a force, friction is matching me. I apply more force, friction matches me again. So the friction is matching the applied force, working hand in hand, until I hit a breaking point. At that point, suddenly it starts to slide much more easily. So it's a lot harder to get them to going, but once they get going, then basically they're running across each other, and it's generally easier in this model. So we differentiate between static and kinetic. Kinetic friction, kinetic meaning movement. We have an object that's moving, that they're actually sliding against each other. I hesitate to say movement. Back to the books here. There is static friction between the workbook and the textbook. They're both moving relative to the ground, but they're not moving relative to each other. So this is static. So just as I pushed on the table, the friction matched me, the static friction is going to be less than or equal to some maximum value. This is the breaking point. Once I overcome that, it's now kinetic friction. Now, these formulas I'm putting up here, basically, they had developed these by, I think, 1790s, and it really hasn't been changed much since. My theory is that because physicists generally don't deal with friction, and engineers have something that work. And those are pretty much the only two groups who care. Now, having said that, there's a group at NC State who is working on trying to come up with something better. But again, engineers have something that work, and they're practical group. It's a general rule. If we did a plot of friction versus applied force, it's going to match. So the friction is going to match the applied force up till I hit a breaking point. So this would be static friction max, at which point it suddenly drops off quickly. And this right here would be my kinetic friction. Almost every textbook I've ever seen has the two values, mu sub s, mu sub k. Mu sub s is greater than or potentially equal to mu sub k. Now, there is a friction experiment that we probably won't do this semester, but there is a friction experiment where I have students trying to find values of mu sub s and mu sub k between two objects. Some of them will have mu sub k bigger than mu sub s. So, a Nobel Prize potentially in the making.
Couldn't mu sub s be smaller, say at the very beginning of that graph?
Mu sub s is indicating where the breaking point is.
Max.
The friction, the static friction could potentially be less than the kinetic friction in this first region right here. But the coefficient is still related to the maximum value. Other questions?
So you were saying that static friction is when it's so much friction that it stops moving?
There's no sliding between the two objects with static friction.
Okay, and then kinetic friction, which is the FK, that's when it's still sliding?
Yeah, the two objects are sliding against each other.
Okay.
So sometimes in a problem, I set it up where first you have to decide, figure out is it sliding or not. And then once you figure out it is sliding, then you use mu sub k. Sometimes I want to just bypass that and I say, just assume it's already sliding. In which case you don't have to show that it's sliding, you just dump straight into its kinetic.
Is static friction usually more, is there usually more static friction than kinetic friction?
The maximum static friction is more than the kinetic in this model.
Okay.
And I say this model, there are two competing models that I'm going to talk about. This is what the textbook uses. This is what we tend to do, but I do want to talk about a competing model. It wasn't a textbook that I first saw in the 90s. One of the textbooks, the previous textbook we used for Physics 251 had a page on it, but still used this model for the actual problems. Anna?
Your graph makes it look like mu sub k is constant once you reach that static friction max, and it just kind of stays level. Is that like regardless of how fast you're walking with the two books, like they're still gonna slide with the same amount of kinetic friction?
Yep. How fast they're moving is not affected. Matter of fact, in that experiment when I talked about that they were changing the surfaces, so the coefficient was changing, one of the things they were looking at was how speed affected it. It was one of those great moments of education. They were pulling it along at different speeds, and they kept getting close to the exact same value for the friction. And one of them said, "This can't be right. We keep getting the same value." I thought, yes, you notice you keep getting the same value, or more, since it's physics. Hey, the experiment worked. How fast it's going does not affect this.
Did they rejoice?
Not as much as they should have. But it was physics, so they couldn't help it, there's some rejoicing there. Other questions?
Could you just briefly explain what F applied means?
F of what?
F applied, I think that's what I'm reading. It's on the X axis. of the
F
curve.
applied, oh, the applied force, that's in, I'm pushing on
Right.
it. So as I apply more and more force, once I hit the breaking point, then I'm only facing kinetic friction.
So that could potentially be a tension force if you were pulling the dad pulling boy on the sled or
Yes.
something, okay.
Yes. It's whatever, everything but friction is doing.
Mhm.
Other questions? Now that Brooke stepped out of the room, you wanna know the answers to the questions? All right, so nook and cranny model. Let's talk about the other one. The attraction model. In the attraction model, it's not that there's one thing bumping against something else, it's that there's one thing pulling on the other thing. So if we look at the surfaces deep down and sort of zoom in a little bit further, there's actually atomic attraction between the molecules that are at the surface. And it doesn't necessarily preclude that, you have more surface area over there. But there's an attraction here, and so what you're doing is you're fighting that attraction. In this model, if we did our graph of friction versus applied force, it's gonna match it step by step until you hit that breaking point, at which point the friction doesn't drop down. In this model, friction is less than or equal to mu y. This would be u sub y. In this, so that's my feeling. I'm not gonna answer this, but yeah. Shut that. In this, there's no distinction between static and kinetic. Now, we have two very clearly different graphs here. It seems like it should be really easy to do. It's not. Again, there's something that's already working. How much do we really need to investigate further? I said they had more sophisticated recording equipment or doing measurements in that experiment, but they're not that sophisticated that there's still error bars on it. So you can look it up online for coefficients, and you might see that use of S for let's say rubber on asphalt. There's a U in there, however asphalt is spelled. I'm going off of memory here. It's somewhere around 0.8 for the static. And kinetic, we'll just say 0.6. Not exact, but it's somewhere in there. What this group is claiming is that 0.8 is not exact. It's actually 0.8 plus or minus, say, 0.15, and that 0.6 could be plus or minus 0.2. And there's a lot of overlap that you really cannot statistically distinguish between the two. But we will pretend that we can. And one other bit. And I asked Ms. Sasson about this as well. Neither of us are aware of any mu sub S value bigger than 1. We don't know of any theoretical reason why it could not be, and there might be some eccentric materials that have been done in a lab that just aren't mass produced, but mu sub S seems to be limited by 1. So, to the best of my knowledge. All right, any questions before we actually apply this stuff?
Sorry.
You do apologize.
So you described that as mu sub y, but it doesn't look like a subscript.
No, there's no subscript over here, just mu.
It's just mu times y.
Yeah.
Okay. I may have misread.
All right. So let's start out on a simple flat surface. Let's make this 4 kilograms. And I'm going to push here with 10 newtons of force. U sub S equals 0.3. U sub K equals 0.2. Initial velocity is 0. And the question is, what is the acceleration? Which tends to be the question a lot of the times in these chapters. We're going to run through facades. First step, force diagram for box being pushed on ground. Now we could throw the ground into it as part of it. We ultimately we don't care about the forces on the ground. Doing that is just for completeness, so I'm going to throw it in there for completeness, but ultimately we just care about the forces acting on the box. But let's go through our checklist. That tongue, as we go through our facades. So what forces are acting here?
There's gravity, there's weight, down on the box, up on the ground. Normal force, up on the box, down on the ground.
There's friction to the left of the box, to the right of the ground.
And then would our 10 Newton force be considered another
Yes, it would.
force?
Ooh.